Okay, this is a little more of a straightforward induction proof. So the proof will be by induction on n. So since we want to prove this true for all natural numbers, 1 would be a nice base case if it works out. So let's go ahead and try that. So we'll say for n equals 1, we have, so now I is going to go from 1 to 1, which really is just one term in this summation. So we can write 1 over 1 times 2. And then our n here again is 1. And then 1 plus 1 is 2. This is true. So P of 1 is true. And then we can say, assume, so here we're just replacing all the n's with k. We're going to assume that this is true. We want to show that same idea, except everything is going to replace n with k plus 1. So this would be k plus 1 up here, and this would be k plus 1 plus 1. Again, we're just substituting in k plus 1 for n in this original equation. So this is our starting line and our ending line. A couple different ways. We could start from this and add to both sides and try to show that we eventually end up with this. That would be one way. Or we could start with the left side of the equation, do some arrangements, and end up with the right side of the equation. That would also work. Let's start with this. So since this is true, we know that we could take all of these on the left side. Let's try to make it look like the left side on our finish line here. So what's the difference between this and this? Well, this has I through k plus 1. This one just has I through k. So this one has an extra term. And what does that term look like? Well, when I equals k plus 1, we have 1 over k plus 1. I'm just going to go ahead and put k plus 2. It's really k plus 1 plus 1, which would be k plus 2. All right, so that's the left side that we've added this term to. And then the right side would be that same k over k plus 1 plus, and we need to add this same thing. If we're going to add it to the left side, then we should add it to the right side. Again, so the reason we know this equation is true is because we're assuming this is true, and the only thing we've done is add this term to both sides of the equation. And the reason we added that term is because now our left side matches up exactly with what it should for our finish line here. 1 over I times I plus 1. Okay, and why do these two add to this? Well, that's how we created this term, is we tried to figure out what term did this have in it that this didn't have. So this and this, these two things are, these two sums are exactly the same except for that final term, which is right here. So once we add that in, then we have the left side here. So now the goal is we need this, and hopefully this is going to boil down to this right here. So the first thing we want to do, we have two fractions. Let's get a common denominator, which would be k plus 1 times k plus 2. So let's multiply this first fraction by k plus 2. We'll have k plus 1 times k plus 2 on the bottom, and 1 over k plus 1 times k plus 2. Okay, and then we add these, so we have, I'm just going to multiply it out here, k squared plus 2k. That's when we multiply these out, and then we're going to add that 1 plus 1 over k plus 1. Now we could just keep going and over, but we really want to end up at this finish line. So here's where we want to try to figure out what's going on. Well, for one, we have a k plus 2 on the bottom, which we do here, but we have an extra k plus 1. And we also see that we have some more terms on this side than we do right there. So at this point, we might realize that, oh, that looks familiar. That's k plus 1 squared. And I'm just going to write it out like this because of what's coming up next, which you may be already noticing. So instead of writing k plus 1 squared, I'm writing it like this because now we have a k plus 1 on top and bottom, and we can cancel out. So now we have k plus 1 over k plus 2, which is what we needed. So since, let me add a few more words here. By the induction hypothesis, we know this right here. Or you could say, even better, adding 1 over k plus 1, k plus 2 to both sides of the induction hypothesis. We know da 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 da. And you could put things like by algebra here. So we've shown equals 1 n Okay, we showed it for the base case, then we showed if we assume it's true, we can prove it true for the next integer as we put those two together, and we've shown it. Now, if this looks messy to you, it really gets at something I tend to do with induction. I tend to have like a rough draft where I try to figure out what everything is happening, and then I have a final draft where I actually write it out. On your homework, it's fine to do something like this, kind of chicken scratch, rough draft, and then add in some words. I do want to see the words, though. That's important. If you just have symbols, you can't really consider it a polished proof or a finished proof. Oh, and I didn't put in my symbol here, whatever symbol you have. Okay, so you do want to put in some words. On a good problem, you definitely would want all this to look very nice and clean. On an exam problem, I'm also okay with the chicken scratch method as long as I can read everything that's going on. So maybe you leave yourself a little extra space for some of these words. But I don't want to just see symbols throughout. I want to see some English words there. Should be able to be read in sentence form.